All right, guys, today we're going to talk about chemical equations, and chemical equations are what we use to represent chemical reactions. You guys remember what chemical reactions are? When matter changes forms, atoms rearrange, we go from one substance and a new substance is produced. So, you guys, let's look at one. So, for example, this would be a chemical equation. I would encourage you guys to write that down. And then from our nomenclature unit that we just went over the previous semester, the idea is that you would hopefully be able to read this. This would be like a chemical sentence. So what you guys were learning were chemical words in nomenclature, and then we put them together in a chemical equation, which you could call a chemical sentence. So this is how you could read it. We should know what that is. Sodium carbonate. And what we would say, we don't want to say plus, we want to say reacts with. So sodium carbonate reacts with, and I'll talk about the two later, but we wouldn't mention that. We'd say react with hydrochloric acid, and then we have the arrow to produce water. We know what that is: water, carbon dioxide, and salt, or sodium chloride. Okay, so guys, let's just kind of break down the parts of a chemical equation. So that's what this is. This is a chemical equation. You could write that down. This right here, you guys should remember from before, is called a chemical formula. Here, you know what, let me use a different color just to stand out a little bit. That's a chemical formula. Right here, these are called phase notations. It tells you what phase, what state of matter it is in. Sometimes chemical equations don't include those, but if it does, it helps a lot. Okay, and then a big one, you guys should know that the small numbers here, those are subscripts. You remember that tells you how many atoms of that particular element are in that compound, or unit of that compound. And then a big one here is coefficients. Those are called coefficients. So, like I said, you guys, a chemical equation represents a chemical reaction. So you guys can think of, here's another big thing. So everything on the left side of the equation are called the reactants. And everything on the right side of the equation are called the products. So, you guys, in order to carry out this reaction, think about what would I need? So we carry out this reaction. What would I need? I would need my reactants. That's like your ingredients. Like if you're making like a pie or something, what are the ingredients you need? Sugar, flour, and things like that. These would be my reactants. So you could describe sodium carbonate, and you guys, even if you didn't know what sodium carbonate is, you guys have it at home in your refrigerator. Well, actually, you might not have that in your refrigerator. You'd have sodium bicarbonate in your refrigerator, but sodium carbonate, and one of the refrigerators called baking soda, but you probably have baking powder in your cabinet. That's baking powder. Sodium carbonate, notice, look, it's a solid. So here's my baking powder, sodium carbonate. And then hydrochloric acid, how would I expect to find hydrochloric acid? I'll remind you guys from first semester, I can't remember if we went over it. AQ, that's something that you're probably not familiar with. You guys will be familiar with this. Look, solid, L is liquid, G is gas, right? AQ, you guys gotta remember, AQ means aqueous. That means dissolved in water. So sometimes you can have a gas, it would normally be a gas. If it's dissolved in water, we'd say it's aqueous. Like hydrogen chloride actually, as a gas, it normally exists as a gas, but when it's dissolved in water, that's how you get hydrochloric acid. And then also you could have other things, solids. Your typical solution is a solid dissolved in water. We would say its state is aqueous. So I need sodium carbonate and I need some hydrochloric acid. You guys see, if I have both of those, the reaction can occur. So that's what I'm going to do. I'm going to use my spatula and I'll use my test tube. So I'll put some sodium carbonate in here. Now, you guys, the good thing about a chemical equation, it can give you a lot of information about the reaction, and you can make some predictions about the reaction before you even do it. So I'm hoping you guys are look at that chemical equation and try to predict, what do you think is going to happen what will you predict to observe? So I have my sodium carbonate, and all I need is my hydrochloric acid. What do you guys predict would happen when those come in contact? So when I do that, okay, what do you think would happen? So look at what's being produced. I don't know if any of you guys picked it up. I was hoping some of you guys would notice, oh look, carbon dioxide gas is going to be produced, what do you think you're going to see when I bring this liquid, this aqueous solution, in contact with the solid? If a gas is produced, what are you going to see? Bubbles! Okay, so we can make that prediction ahead of time, and sure enough, you guys who see it there, and you guys, I'm actually not demonstrating good lab skill. I should have eye safety wear on. Obviously, I'm working with some acid here, but and you guys can see the bubbles that are being produced. Okay, so that reaction's still going, and we know the reaction's still going. We've got bubbles still being produced. Hopefully that's okay. All right. So obviously, you guys, what were the bubbles? And we can get that from the equation. When the bubbles, carbon dioxide gas that was being given off. And so you guys, what do I have left? Okay, so now the reaction's done. All right, we don't see any more carbon dioxide being produced. You guys, what do I have here? Well, you guys just look at the product side. I've got water and I've got salt. Well, the question is, well, where's the salt? I don't see the salt. Oh, it's aqueous. The salt's in the water. It's an aqueous salt solution. So that's kind of typical when you have like a carbonate with an acid. You're going to form carbon dioxide, water, and then a salt. Okay? So here's, you guys, what's happening. In a chemical reaction, all you have is a rearrangement of atoms. The atoms you start with, or the atoms you end with, are just rearranged. So you guys, these dots, these magnetic dots, represent atoms. You can imagine the two black ones are your sodium atoms. There's one carbon atom and 3 oxygen atoms in one sodium carbonate unit. And then hydrochloric acid, the green is the hydrogen, the yellow is the chlorine. But notice it takes 2 hydrochloric acid molecules to react with 1 sodium carbonate molecule. See that? See where the coefficients come from? This says 2 of these reacts with 1 of those. And so what's going to happen, look, I'm going to end up producing water. Oh, so I need 2 hydrogens. Remember my hydrogens. So what's going to happen is the bond between these are going to break. Okay? So we have to break bond. That actually requires energy. And those 2 hydrogen atoms are going to combine with one of these oxygen atoms. So it takes energy to break. So basically these molecules have to collide with enough energy to break old bonds. And then when new bonds form, energy is given off. This is ultimately an exothermic reaction. And how would I know if I feel this? It's actually warm, indicating heat energy was given off. So the point is, more energy was given off when new bonds formed than the energy that was required to break old bonds. So overall, there was a net release of heat energy. So it forms water. I'm also forming carbon dioxide. So it's going to be the 1 carbon atom is going to combine with just 2 oxygen atoms. I see this is carbon dioxide. It would look like this. You guys remember our shapes. Remember water is bent shape, carbon dioxide is linear. And then I'm going to form NaCl. The Na and the Cl are going to combine together. Oh, you know what? This wasn't even properly balanced. This is a good point. You guys notice we have to account for all of our atoms, so you end up producing. You guys remember how that forms? You remember it's alternating. Remember, ionic compounds are alternating positive and negative ions, so it would kind of look like that. So what the whole point is, guys, you notice the atoms we end up with are the atoms we start with. There's a conservation of matter. All that happens is a rearrangement of atoms. So what you guys are looking here is what's called a balanced chemical equation. And you balance chemical equations by adding what are called coefficients. And you guys see how it wasn't properly balanced before. There needed to be a 2 here. So that being done, now the same amount and type of atoms I start with are equivalent to the same number and type of atoms I end with. So you guys, we're going to practice how to balance a chemical equation. That's essentially what you guys are going to be doing in the assignment associated with this video lesson. So, guys, let's use this. You guys write this down. Okay? Now, here is not a balance. If you guys don't see coefficients, you guys notice there aren't any coefficients. Now, what that could mean is the coefficients are just 1 if you don't see a number. But then you should be able to look at that and be able to tell, is this equation balanced? Are the same number and type of atoms on the reactant side the same number and type on the product side? Here's how you guys can, here's what can help you guys to do that. What I want you guys to do here initially, until you guys get better, is I want you guys to draw atoms. So, oh, by the way, guys, this is a very important, probably the most significant, one of at least two significant chemical reactions in life. Guys, look at that. You guys know what that reaction is? That equation is representing what reaction? It's key to life. I know some of you guys probably the first thing you think is photosynthesis, but you got to remember, this is actually the opposite of photosynthesis. You guys know photosynthesis is the process by which plants take up water, right? You got to water plants, and they absorb carbon dioxide, and then they form, and then the plant utilizes the sun's energy to rearrange those atoms because it's an endothermic process. It requires energy to do it, to form, you guys remember glucose, which is, right, the like fibrous material or plants that animals, including ourselves, can eat, and then what do we end up giving off? What does the plant end up giving off is oxygen, right? That's why you want a lot of plants around, because it just, you know, improves the oxygen in the air. And then also, so if you guys notice, we're not going this way, we're going this way. This is a process in which glucose reacts with oxygen to produce carbon dioxide and water. You guys, what's that? That's cellular respiration. Remember, that's what's happening in the mitochondria. You guys remember the powerhouse of the cell. That's what's happening in the mitochondria of all the cells of your body. And so you think about it, we take in glucose food items, right? And if we don't take in directly glucose, our body can kind of break down different food items to produce glucose, reacts with oxygen. We're breathing in oxygen, and then cellular respiration occurs, and what are we breathing out? Carbon dioxide. And then you guys, if you breathe on a mirror, what are you guys going to notice? It's going to fog up, indicating you're breathing out water vapor as well. And then that process is exothermic. It generates energy, and then your body is able to store that energy. You guys remember, produces ATP, so trying to make a little connection with biology here. And then your body can utilize that energy for all your necessary bodily functions. All right, so anyways, this is cellular respiration, but it is not balanced, and I'm going to show you guys how. So guys, what I'm going to have you guys do is represent all the atoms here initially, okay? So look at glucose. So look at the glucose molecule. This is what we should be able to bring up. Glucose has 6 carbon atoms. So I'm going to draw 6 carbon atoms, and I'm going to show. And you guys, you don't have to draw it the way. We don't care about Lewis structures right here, so you're not going to necessarily draw it. All we want to do is account for all of the atoms. So we notice it's got 6 carbon atoms. Notice, look, it's got 12 hydrogen atoms. So I'm going to draw 12 hydrogen atoms. Notice I'm going to show them touching each other, indicating that they're bound together. But you guys, this isn't actually how it would look. But once again, I'm not too concerned about that. I just want to account for it. And then it has 6 oxygen atoms. Okay, so that's one glucose molecule. Look at one oxygen molecule. That's a little easier. It's just 2 oxygen atoms. Okay, and then it would produce carbon dioxide, which contains 1 carbon atom and 2 oxygen atoms. And then water is 1 oxygen atom and 2 hydrogen atoms. Okay, once again, don't worry about if those don't look right, and they don't. Like, you guys, glucose isn't like one big old boxy molecule. It actually forms a a ring. But anyways, don't worry about that. So hopefully you guys can look right off the bat. See, now if we have a visual representation, you guys should be able to see clearly the atoms aren't balanced. You guys can see clearly we have much more carbons, hydrogens, oxygens on this side than we do on this side. It's an unbalanced reaction. What we have to do is balance this chemical equation. So here's how to do it. You first choose an atom, choose one atom, and you focus on one atom at a time. What you should always do is save hydrogens and oxygens for last. The reason is because hydrogen and oxygens are usually in a lot of different places, and it'll get kind of confusing. So don't do hydrogens, oxygens. With the exception of hydrogen and oxygen, choose one atom to focus on. Obviously, what's your choice here at this point? Wouldn't it just be carbon? So then you count. How many carbons do you have on the reactant side? How many carbons are you starting with? I'm counting 6. So I'm starting with 6 carbon atoms. And at this point, how many are you ending with? You're only ending with 1. So obviously, it's not balanced. So then what I'm going to do is, so I'm going to focus on carbon. I'm going to look at where's carbon located. You should be able to find an atom where it's only located in 2 spots. One on the reactant side and one on the product side. So carbon's in my glucose here and carbon's in my carbon dioxide here. So I'm going to focus on carbon. So I look, with my glucose here, okay, I've got 6 carbon atoms. With my carbon dioxide here, I only have 1 carbon atom. So the question is, do I need more glucose molecules or more carbon dioxide molecules in order to balance my carbon atoms? Hopefully you guys would realize, oh, I need more carbon dioxide molecules. So the question is, how many carbon dioxide molecules do I need so that I end up with the 6 carbon atoms that I'm starting with? Well, if you guys look, carbon dioxide, each carbon dioxide molecule only has one carbon atom, so how many total carbon dioxide molecules do I need? When you guys agree, you need a total of 6, and if you don't see it, you just keep drawing. Now notice, I'm not just drawing carbon, I'm drawing the entire molecule, because carbon is found in carbon dioxide. So I keep drawing the amount of carbon dioxide molecules such that I have 1, 2, 3, 4, 5. I still don't have enough carbons until I have the 6 carbon atoms I'm starting with. See, it took 1, 2, 3, 4, 5, 6. So now I count 6 carbons, my carbons are balanced. Now I add coefficients. Well, how many glucose molecules do I have here? I only have 1. So I'll put 1. And you remember, we just started with 1 initially, and then we add them as necessary to make them equal. So I have 1 of those, and how many carbon dioxide molecules do I have? 1, 2, 3, 4, 5, 6. So I put 6. Okay? So now my carbons are balanced. Okay? So now at this point, now I move on to another atom. Notice we're just focused on one atom at a time. So here's what you guys want to do. So you're either left with hydrogens or oxygens. Those are the only other atoms. What you would want to do at this point is choose an atom where it only needs to be balanced on one side. So if I look, see now if I chose oxygen, let's say I want to focus on oxygen, look, oxygen needs to be balanced here and here. Notice these are 2 places where oxygen occurs that doesn't have a coefficient. So I don't want to do that. That gets kind of confusing if I do that. But now look at hydrogen. If I chose hydrogen, look, hydrogen only needs to be balanced here. Notice every other place it's already got a coefficient associated with hydrogen. So I only need to balance it here. So I'm going to choose hydrogen. So now I need to figure out, okay, what's the coefficient here? So what do? I look to the other side and I see how many hydrogen atoms am I starting with? And you just count. There's 6 and 6, that's 12. I'm starting with 12 hydrogen atoms. So if I'm starting with 12 hydrogen atoms, I need to end with 12 hydrogen atoms. So once again, if hydrogen is only found in water over here, the question is how many water molecules do I need total in order to end up with 12 hydrogen atoms? Let's say you can't do it in your head, so then you just draw it. So once again, you notice I'm not just drawing hydrogens, I'm drawing the entire water molecule. So anything that's under reaction species should be that entire molecule. So I keep drawing waters until I end up with 12 hydrogen atoms. And if I do that, I think I got enough. I've got 2, 4, 6, 8, 10, 12. That's my 12 hydrogen atoms. So how many water molecules do I need? 1, 2, 3, 4, 5, 6. That's 6. So I'm going to put a 6 here. And now my hydrogens are balanced. Now you guys see if I do it right, now the last atom I only need to balance in one place, which is oxygen. So what do? If I need to know how many I need here, I look to the other side. Now, so I look to the other side, okay? So I want to see how many oxygen atoms did I end with. So I have to count all the oxygen atoms I end with. So if we look, I got 2, 4, 6, 8, 10, 12. I've got 12, but I also have 13, 14, 15, 16, 17, 18. I end up with 18 oxygen atoms. That means I need to have started with 18 oxygen atoms, okay? You guys remember, matter's not created or destroyed, it just changes form. So whatever you start with is what you end with. So, but you guys, all 18 oxygen atoms don't have to come from O2. You guys got to keep in mind, we've already accounted for some oxygen atoms. Look at how many oxygen atoms we've already accounted for. 1, 2, 3, 4, 5, 6. So I have to end up with 18. I already have 6. So how many oxygen atoms do I need to get from O2? 18 minus 6 is 12. I need 12 oxygen atoms from here. So once again, what do? I keep adding the number of molecules necessary to get the number of atoms I need. So I've got 2 here. You guys remember oxygen always appears as pairs, so I have to write them as pairs. And remember I needed 12 oxygen atoms, so let's see, 2, 4, 6, 8, 10, 12, yep. So the question is, how many of these O2 molecules did I need to get the 12 oxygen atoms? 1, 2, 3, 4, 5, 6. So then I put a 6 right here. And what you would want to do is, the last thing you want to do is just do one final check to make sure everything is nice and balanced. Now let me show you, and how you can do that, you just start counting atoms. You guys, and do the carbons first, see if the carbons, and then count the hydrogens, see if the hydrogens, and then count the oxygen, count the oxygen. So you guys, ultimately I want you guys to start this first assignment by drawing it just like this, but ultimately you guys are gonna get, after this assignment, I'm not gonna require you guys to draw the atoms because you guys can actually kind of figure it out, that you guys will start getting better at this. Now check out how I can count the atoms without actually having to draw them. You could just look at the subscripts and the coefficients. So now if I wanted to count to make sure it's all balanced, here's what I could do. I could count my carbon atoms. Look what I can do. I'm like, it's got coefficient, subscript of 6, coefficient of 1, I just multiply those. 1 times 6, it's got 6 carbon atoms. See that? 6 carbon atoms. And then I look here, carbons here. You guys, if you don't see a subscript, that's a 1. So I have a 1 times a 6. Remember, you always multiply the subscript times the coefficient. So that means I have 6 carbon atoms. See? So that's good. 6 and 6 is good. Now let's say I look at my hydrogens. What can I do? Multiply the 12 times the 1. How many hydrogen atoms do I have on this side? I have 12. 1 times 12. And then how about on the product side? Look, 6 times 2 is 12. See, I didn't even, this is a way you could do it without having to draw it and then look at the individual atoms. And then lastly, oxygen. What do? Subscript times the coefficient. There's 6 times 1 is 6. Look, subscript times the coefficient. 2 times 6 is 12. 12 and 6 is 18. So there's a total of 18. Let's see how many I ended up with. 6 times 2 is 12. 6 times 1 is 6. 12 and 6 is 18. 18, 18. It's all good. This is a properly balanced chemical equation. And you guys, we have to have properly balanced chemical equations in order to do further calculations, which we're going to learn in subsequent lessons. All right, guys, that's it for chemical equations. Hopefully you guys will learn how to balance those. Practice. We'll see you guys next time.